were discussing about the capacitors, its terminal relationship, voltage current relationship. This was the thing. If you indicate the voltage across the capacitor with this polarity, show the current also in this direction, and if this is C, then I t, this is the differential relationship, C dV dt is the thing. And also if you excite the capacitor with some current source, this from this equation only we found that V t at any time will be minus infinity to t into I dt. This will give you Q by C. This is also the expression of the voltage, and then we have shown that if this excitation current source is a reasonable function, then the voltage at t equal to 0 plus will be same as voltage at t equal to 0 minus, that is voltage at t equal to 0. Using this, then we solved this circuit in last lecture, that is, if there is a voltage source, battery, and if you have a switch and you want to charge a capacitor, this is one of the simplest circuit. You do it, and if the capacitor is initially uncharged, that means V 0 minus was equal to 0, and you are doing the switching at t equal to 0. This is the switch. Then the expression of the voltage across the plate of the capacitor, that is this voltage at any time t, was shown as e to the power minus t by tau. Tau is the time constant, which is the product of R and C. Similarly, the expression of the current at any time t will be E by R, and it will exponentially decay, and finally steady state current will vanish. These things we have seen, and the energy stored in the capacitor at any time t will be of course equal to half C V square, that instantaneous value of the voltage. In this case, of course, the capacitor will finally charge to this voltage, that is E. This is V t, and the current, if you sketch, this is T. Current will go up suddenly to a value E by R. This level is E by R, this one, and then it will exponentially decay, and finally no current can exist in this circuit. However, capacitor will get charged. Now, today we will see how this energy can be retrieved from the capacitor. See, so for this what I will do is this, this is your initial circuit. I will just redraw it in a different fashion. This was the capacitor, and here you want to retrieve the energy stored in the capacitor in a load resistance R. This is plus minus E. So, when you connect the switch, when the switch was in the neutral position, neither connected to A and B, there was, I will presume, V 0 minus was 0 earlier, it was 0, but if you close it here, then the capacitor will finally charge with the voltage capital E, if you wait sufficiently long. So, my next problem, I will without much saying, I will state the statement of this problem is like this. You have a capacitor which has been, and its voltage across any time I will indicate by this polarity and this one, and I will say this capacitor has an initial charge is equal to some value, okay, some finite value. It has been charged by some other circuit, and let this value be V naught, suppose I say. So, capacitor is charged like this and I will make a circuit this way. This is the discharging of a capacitor. This is my load resistance, and although there is apparently no active source present like battery or current source, but mind you, if you close the switch at t equal to 0, then this energy will be dissipated in R L. So, we started with the energy half C V naught square. So, it will act as a source, okay? And we want to find out how the current in this circuit will flow and what will be the how the voltage across the capacitor. As it discharges, you know, it will lose voltage, how the voltage decreases. So, anyway, to solve this circuit now, I will say that at t equal to 0 you have closed this circuit and let at any instant of time the current is I t in this circuit. The moment I show that, I should not forget to show the polarity of the voltage drop across R L. It will be plus minus like this, and voltage across the plate of the capacitor is like this. Therefore, I will apply KVL in this circuit. Okay. So, this is the current I have assumed, and I will then say the this voltage to be plus minus like this V 0, and okay, that is fine. Now, I will write down the KVL. What is KVL? So, IT is mind you here if you look let it be like this. I thought I will change it. Suppose I have done like this, then I have assumed the current to be like this IT. Then you recall that this is correct, plus minus, if current enters here, this is C and this is V, then I is equal to C dV dt. Therefore, here the current is leaving the positive terminal, or I can say that minus I is entering through this plus to this place, is not, this is one and the same thing. So, I should write minus I, this step is crucial, minus I to be consistent with this polarity of this voltage current relationship of a capacitor. So, minus I is really entering, and this I can write it to be C dV dt. This is very important to understand. You should be consistent with this. Since I have assumed the current to flow out like this, no problem, but then while writing I equal to C V dt, you must write it minus I is entering through the positive terminal of the capacitor. So, that current is C dV dt. Okay. Now, so I will write down the KVL equation now in this equation. What is that? This will be, you start from anywhere you like, for example, this will be this drop R L into I will be nothing but R L into I is minus C dV dt, I is minus C dV dt. So, R L into C dV dt with a negative sign like this. Then you start your journey from this point, say minus to plus V t KVL, you write KVL will be this to this. I have defined it to be this polarity minus to plus V, then with this minus R L into I, is not, plus to minus, and I have reached the starting point that is equal to 0. Then what I do, I substitute the value of I. This is the value of I. So, it will be V minus R L, and for I will write minus C dV dt, and that will be equal to 0, or you will get C into R L into dV dt plus V is equal to 0, and then dV dt plus 1 over C R L. R L I have not written R simply to tell you that I am using the energy in a load resistance, that is all. It could be R as well. This is equal to 0 into V. So, once again a first order differential equation, and the solution will be, you multiply with the integrating constant C R L 1 over C R L dV dt plus of 1 over C R L into e to the power t over C R L into V is equal to 0, or I will say d dt of e to the power t by C R L into V t is equal to 0. Therefore, this fellow must be a constant. Therefore, e to the power t by C R L into V must be a constant to be determined from the boundary condition, or I will say voltage across the plate of the capacitor should be A into, this is the integrating constant, okay, or constant, as you can see, minus t by C into R L. This will be the solution. So, this is how capacitor voltage will decrease, it will decrease exponentially. Now, the question is how to determine the value of A. The value of A is to be determined from this boundary condition. Since V 0 minus is equal to V 0 plus is equal to V 0, and that is given to be V 0, capital V 0. Therefore, by substituting this boundary condition, you get A to be equal to V 0, because T 0 this is 1 and V is equal to V 0. So, this will be then A is V 0 into e to the power minus T by C R L. I am sorry, I should not write it like that. So, this is equal to V 0, fine. So, this from this you get, so solution then becomes V t is equal to V 0 from this equation into e to the power minus t by C R L. This will be the voltage across the plate of the capacitor at any time t. And what will be this current I t? I t, once I get V t, I will use this formula to get I t. So, I t at any instant of time, it should be minus C into d dt of V I have got this. So, put that value V naught into e to the power of minus t by C R L, is not, this will be the thing. And if you see this one, it will be minus C was there, and then differentiating. So, minus 1 by C R L will come out. So, minus 1 over C R L is not into V naught and e to the power minus t by C R L. So, the expression of the current will be then I t is equal to, this C goes minus minus plus. So, it will be V naught by R L divided into e to the power minus t over C R L. Of course, without differentiating I could easily get it, because you see the voltage across the resistance is same as voltage across the capacitance V. So, V divided by R L, V is V naught into e to the power minus t by C R L by R L will give you the current, is not? That is I t is nothing but V t divided by R L will also give you the same expression. Therefore, the voltage across the capacitor will decrease exponentially, and if you sketch that, you will get this way. If you sketch, always make a habit to sketch the transient condition voltage and current in a circuit. So, capacitor voltage was initially it was T 0 minus, it was some V 0. It has to start from this, capacitor voltage cannot change instantaneously, and then this voltage decreases exponentially, whose equation is V naught into e to the power minus t by time constant C R L. C R L is the time constant here. Similarly, here the below this with the same time scale, if you sketch the current I t in the circuit, current will be, earlier there was no current T 0 minus, it was open. So, current was 0, then suddenly it goes up. In a capacitor, current can't have a jump, whose values will be V naught by R L, and then this fellow also decreases. And for obvious reason, can you tell me what will be the value of this integration, that is I square R L dt t equal to 0 to infinity. Suppose somebody integrates it. First of all, what this physically means? It means the energy, total energy dissipated, this expression is nothing but total energy dissipated in R L, and I am not calculating this, it must be equal to half C V naught square. You started with this energy, only this much energy can be dissipated. Clear? Therefore, total energy dissipated in R L is this one, no matter what is the value of R L, this much amount will be dissipated in R L. Therefore, we have considered how to charge a capacitor, then how to retrieve that energy from this capacitor for practical use. Of course, this is not a very good use. If you connect a lamp, the lamp will glow, it will get dimmer and dimmer as the voltage across the lamp decreases. But nonetheless, some mechanism I have could be found out by which it can be done, charge a capacitor to some voltage and then retrieve the energy from the capacitor when you need it. We will see much more smarter circuit for using the stored energy in a capacitor at a later stage. For the time being, this you must very clearly understand. In this case of this circuit, once again I am telling this point to be repeated. How did I do it? I told this point, that is negativity, why it comes. You remember the terminal relationship of a voltage across the capacitor at any time t and the relationship of current. If you assume in this fashion, then only I is equal to C dV dt. Now, in this problem what I have done, I was served with this capacitor, I will show with a curved one plate. So, that at no point of time you confuse it with a battery. So, this is a capacitor and its initial charge and voltage across the plate of the capacitor I have decided to be like this V t. And I told you that V 0 minus was equal to some V 0. This point I am repeating. Now, here is a switch S and I have connected a resistance R L. And at t equal to 0, this is closed. At t equal to 0, this is closed. Then at any time t, I am free to choose the direction of the current, do not mind. So, I t, but once you choose this I t, you cannot play with these polarities, this is fine, R L into I. What is the KVL in this loop? KVL in this loop, you start from this minus 2 plus V t I have assumed with this voltage rise, then there is a voltage drop, that is minus R L into I, and you have come back to same point, this must be 0, this is the KVL. Now, the question is I have to form a differential equation involving V only, differential equation I want to form. Now, the question is what is the relationship of the current and the voltage? Now, here you concentrate, this I is like this I have assumed, but so what is the current entering the positive terminal of the battery? I must say it is minus I, and this minus I will be C dV dt. That is the point to be noted, and that you put it here and then proceed. I hope you have understood this point very carefully. So, this is the point. Similarly, I mean similar thing may be, suppose somebody has an inductor, I say this is the current, okay, and somebody told that I will assume the voltage across the inductor to be like this, this is L. He is absolutely fine, you can choose your direction of the current or voltage, but once you do that you cannot play with this. Then I will say okay, through the plus terminal minus I is entering. Then the terminal relationship of this should be V is equal to L of d dt of minus I. I think you have got the point. Now, anyway, so capacitor charging, capacitor discharging we have considered. Similarly, inductor charging and inductor discharging we have considered. And there will be, as you know, several problems, interesting problems involving L and C can be formulated. I will highlight some problems maybe in the next lecture, but another important thing with RLC, with LC particularly, I would like to point out. Before that, so I have got inductor, suppose I write it here, inductor L, and on this side I will write capacitor. See, this is what the terminal condition of an inductor is, plus minus V, and V is equal to L d I dt. While forming the differential equation, we will write differential equation, not integral differential equation, better, because we will be better solving a pure differential equation. That is why this notation. For capacitor, it was like this, plus minus, show the current like this, I, C, and voltage, the relationship I will be equal to. This is how I and V are connected in a capacitor, in an inductor. Now, we ask ourselves and consider a resistance also, resistance. That is R, this is I, this is voltage, and V is equal to R I. Here no differentiation, that is why it is memoryless. This has got a memory, it requires previous knowledge of voltage, and this has also got a memory, that is fine. Now, I will use a term called whether I would like to investigate whether these three elements are linear or not. Are these elements linear or not? Okay. To test the linearity of a particular element, what you have to do, you have to see that whether superposition principle is satisfied. If it is satisfied, then I will say it is linear. Now, how to apply the superposition theorem? Superposition theorem tells that if you do not apply any signal to this element, by the term any signal means I have not applied any voltage. Suppose for an inductor V is input and I is output, I say V is input signal and I is the response, is the output or response. This point you listen carefully. The question is, if you do not apply any input signal, then this output I must be 0. Okay? That is the first thing for superposition. V is equal to 0, I must be 0. Then what you do is this is called principle of homogeneity. For any linear system, for example, in a resistance, applied voltage is 0, I is 0, so obvious, V is equal, I is equal to V by R. So, V equal to 0, I equal to 0. But here if V is equal to 0, I may not be 0. Why? Because it is differentiation. An inductor can sustain current when it is kept short circuited without loss of any principle, is not? If I is 5 ampere constant in an inductor, how it can be? If I say this is L and somebody draws a circuit like that 5 ampere, is it possible? Yes, very much it is possible. Most probably you have charged the inductor from some source and kept it shorted. This we explained earlier. Therefore, even so, what is the voltage applied between these 2 points of the inductor? 0, but still there is current. Therefore, an inductor with initial current cannot be linear. Okay? Because it will fail this test. V is equal to 0, I may be present in an inductor. This you must think about. And this equation also tells you V 0 does not mean I is 0, I may be a constant, dt of a constant thing is 0, including that constant value to be 0. Therefore, this is homogeneity condition, This must be satisfied. And the next condition is that, so this is required. If you test this and this is not following, then you say no, it is not a linear element, no other test is necessary. But if it satisfies this, then also you test for superposition. Superposition, principle of superposition. What does it say? It says that if you apply a voltage V 1 across the inductor and it gives a current of I 1, then if you apply a voltage of V 2 and separately it gives a current of I 2, V 1 V 2 are different, then superposition principle demands that when you apply V 1 plus V 2, the current in the circuit should be I 1 plus I 2. If this is true, then I will say inductor is a linear device. Of course, inductor will fail this test, the first test, if it has got initial current. Therefore, for testing an inductor for linearity, you must ensure there is no initial current in the inductor. Got the point? The proof of this is very simple. When you apply V 1 voltage, see, let us follow this principle. Oh, I will write it like this: response in an inductor current I 1 t, you apply V 1 only, this one, V 1 alone. So, I will also draw the circuit, so that no confusion remains. You have applied a voltage V 1, this current is I 1. So, I 1 will be equal to 1 by L minus infinity to t. Or say minus infinity to 0 minus is 0, it has to be. So, I will write it then 0 to t, is not V dt, because I have assumed previous to that no voltage has been applied. So, this is the thing I will write, or you can write minus infinity also. Let me see. So, when you have applied V 1 voltage, this will be the current in the inductor. When you apply a voltage V 2, the current in the inductor will be V 2 dt by L 0 to t say, and this will be equal to I 2 t. Now, you just add these two equations, add, and you get I 1 plus I 2 will be equal to 1 over L 0 to t, and these two will add it up. But this current I 1 plus I 2 will be the current when you have applied V 1 plus V 2. So, when you apply V 1, current is I 1, when you apply V 2, current is I 2. When you apply V 1 plus V 2 together, I do not know, I write current will be say I 3 t, and I will write it like this 0 to t V 1 plus V 2 into dt. If you separate these two integration, it will give you I 1 plus I 2. Therefore, the conclusion is an inductor without any initial current will be a linear device. Got the point? Similarly, we will see that a capacitor without any initial current will behave like a linear element. We will consider this in the next class. Thank you.